Hi, my name's Fred Zelt. I'm a geologist and cyclist living in Pittsburgh. And today I'd like to share with you a couple of great bike trails in northwestern Pennsylvania and also the geology of the landscapes in that area. We have lots of great topics to share here. So let me share my screen and get the recording started with the presentation. There we go. And I'm going to minimize the talking head up here so it's not in the way as much. Okay, this is part of a series that's hosted in 2022 by Venture Outdoors and Earth Science Excursions, and I'm recording this in May of 2023, May 23rd. There are 25 bike trails longer than 10 miles in western Pennsylvania, and the two that we'll highlight in this presentation are circled in the black boxes and the heavy black circles on the map you can see in northwestern Pennsylvania. Part of a series of 25 rides that we're hosting. And we've organized these 25 great bike trails into 6 themes of different landscapes and geology. We started with the Allegheny and Ohio River Valleys theme circled in blue. This is actually the 5th one. And the theme of these two is it's the glaciated part of northwestern Pennsylvania. So this is the glaciated edition. It's the 5th one that we'll put on YouTube and share publicly. The Pennsylvania Wilds will be the 6th of these that we create. And we're sharing these publicly not to try to promote the Venture Outdoors bike rides this year. They're pretty much all sold out. We're sharing them to raise awareness of the 25 great bike trails in western Pennsylvania and adjacent states, and give people a little information about why the land is shaped the way it is and some of the geologic history of this highly varied area. So the 2 trails here are the Karl Boyes Trail in Presque State Park, right up on Lake Erie, and the Stavich Bike Trail that actually goes off into Ohio too. It's part in Pennsylvania, part in Ohio. And our objectives are to, again, increase awareness of the 25 great trails. This is the talk where we'll speak about ancient climates that affected the rocks that are in our landscape. We've touched on that briefly in the other talks, but this time we'll go into it in some detail. We're also going to talk about the Great Lakes and Lake Erie. We'll talk about why the Great Lakes are shaped the way they are, how they were formed, why Presque looks the way it is, and it's such a unique feature in Pennsylvania along the shoreline. And then we'll talk about the Stavich Bike Trail and interurban trolleys that existed before cars. You can see the agenda goes through those topics pretty much in that order. So here we go with a bit of climate. Now, when people talk about climate, often this is what they're talking about, just the last 140 years. Every year, this chart is renewed with these research organizations' estimates of average annual temperature, global temperature in the prior year. You can see there are research institutions shown on this chart from the UK and the US. And this is as far back as there have been global confident thermometer-based measurements. So it's not through all of geologic time. When people say this year was the hottest on record, they're talking about the last 140 years or so, these global thermometer-based measurements. There were some ups and downs during this first part of this period, but since about the 1970s, there has been a pretty steady and significant increase of about 1 degree C in global average temperature. And if we look at some detail of that, what appears to be a lot of noise in this chart, some ups and downs, actually makes more sense. So this is that more recent part of the chart. And this time the colors indicate the red and blue are El Nino versus La Nina years. There's an oscillation in oceanic circulation patterns in the Pacific. There are neutral years in black, and then volcanic years. Often when a major volcano goes off, the next couple of years will be a little bit cooler than before or after, temporary effect. So if you just look at the La Nina years or the El Nino years, you can see that they form separate trends here. And some of what appeared to be noise in the chart actually makes more sense because those circulation patterns also affect global climate. Okay, now let's look a lot farther back in time into the geologic past. And to do that, we'll first look at some data that come from ice cores that were drilled in Antarctica and Greenland. So here's the business end, the bit of a core barrel. This would spin down into the ice, cutting the ice around the edges of this and preserving a core of ice in the center. And here you can see a scientist examining one of these ice cores. When snow accumulates to a depth of 50, 100, 150 meters, it consolidates into ice and it traps lots of bubbles. So the bubbles in this ice are little capsules of atmosphere. So you have both the snow that fell and formed ice eventually, and you have little capsules of atmosphere preserved in these ice cores. And there you can see an ice core library in the picture. And the chart shows thousands of years before present, so going back in time from right to left. And then the blue is not a direct measurement, it's a proxy measurement for temperature. And the red is a direct measurement of carbon dioxide concentration in those little trapped bubbles in the ice, those little capsules of atmosphere. So that's a direct measurement. And we'll talk a little bit about the proxy measurement and the CO2 measurement, why we can have some confidence in those measurements in these ice cores. And then we'll come back to this chart and talk about the chart in detail and what it means for ancient climates. First, with stable oxygen isotopes, there are two stable isotopes, 16, 18, light and heavy one being 18. And when seawater evaporates, it tends to favor the light isotope. So clouds are a little bit isotopically lighter than seawater. And when there's precipitation, when there's rain, that favors the heavy isotopes. So the clouds, as they work their way, water vapor works its way from equatorial warm areas where water evaporates a lot to poles, it gets the clouds, water vapor gets isotopically lighter and lighter, so that snow in polar areas is especially light isotopically. And that effect of preferring the heavy or light isotopes in some precipitation or evaporation or in chemical reactions, that's called fractionation. And it's temperature dependent. So you can use the degree of fractionation as an indication of the temperature. The next chart here is shows a relationship between isotopic composition on the vertical axis and temperature on the horizontal. So you get an idea that you can use these stable oxygen isotopes as a good indicator of temperature. And because there's oxygen in the water that's in ice, in these ice cores, we can use ice cores for this, but also in the fossils of animals that lived in the seas and seas today and in ancient seas, we can use their fossil shells because they're calcium carbonate, CaCO3. We can use the oxygen in their fossil shells to get an idea of ancient climate too, going back hundreds of millions of years. Now let's talk about CO2 for a minute and why we can have confidence that the ice bubbles, the air trapped in those actually is reflecting atmospheric concentrations of CO2 and other gases. On this chart in the boxes, you can see ice core data from a place where snow is accumulating relatively rapidly, so there's very young ice, and ice in age that overlaps with atmospheric measurements of CO2. And you can see that those overlap really well. So we can have some confidence then that these little bubbles are reflecting atmospheric concentration of CO2. Here's another look at the same type of data. This goes back 10,000 years. Ice core data in the blue and green, and then the red indicates more recent direct measurements of CO2 in the atmosphere. This chart's a few years old. Actually, atmospheric CO2 is up around 410 or 15 parts per million now. And you can see that through this past interglacial cycle that we're in, CO2 has increased quite a lot in the last couple hundred years. It's a very rapid rise, and a large rise too, when you look at the magnitude of it. Okay, I promised to look at this chart in more detail. Now you have seen that the blue is not a direct measurement of degrees C, it's a proxy measurement. And you can see the degrees C estimated from the proxy. The divisions are 2 degrees C on the right. On the left is the axis for the CO2 concentration measured directly from those bubbles in the ice. And this goes back over 400,000 years, this chart. So you see that there are these big changes, big swings. We're currently in an interglacial period. There are glaciers in Antarctica and Greenland, but not all through Canada, not through Northwestern Europe and Russia like there were in the past. And you'll see a map of that. So we're in an interglacial period now. There have been other interglacial periods. The last maximum of a glacial period was about 18 or 20,000 years ago, and we've come out of that glacial period since then. So you can see that these major interglacial and major glacial periods have been timed or spaced at about every 100,000 years for the last 400,000 years, actually going back about 1 million years. We'll see another chart for that. And then there's a higher frequency oscillation in global climate superimposed on this. These are all natural climate cycles. We'll talk about what's thought to be the origin of these. I'll also point out that when you look in some detail in these natural cycles, going out of a glacial cycle into an interglacial cycle, it's a relatively rapid transition. It's a slower and more stepwise transition going from the interglacial into the glacial cycles in the past. And going from glacial to interglacial, these warming periods, natural cycles, sometimes when you look at the data really closely, the temperature proxy goes up first. Sometimes temperature and CO2 go up together. So they're not always completely in sync. And these are driven, again, by something, they're natural cycles, and we'll talk about the origin of those later. The other thing I'll point out is there's so much ice locked up in glaciers during these the depths of the maximum glacial periods, that sea level rises when that ice largely melts going into the interglacials. So the sea level rise in the last 18, 20,000 years, from then to about 12,000 years ago, global sea level rose something like about 120 meters on average, different in different locations, but about 120 meters. So each of these surely has the same type of sea level rise and fall, with more and less ice accumulated in these glacial interglacial cycles. And these kinds of cycles have happened farther back in time too, and we'll talk about that as well. I promised to look back farther in time. So the chart we were just looking at only went back about 400,000 years. This chart goes back over 500 million years, but it's a little tricky because the lateral scale changes a lot. So the vertical axis is degrees Fahrenheit on the right, or degrees C on the left from those temperature proxies, where it's shown in blue here. They're from ice cores, oxygen isotopes from ice cores. And then the black are from marine fossils, tiny marine fossils going back quite a ways, maybe some larger fossils going back farther, but they're marine fossils that go back over 500 million years. And so that's the basis of the proxy of the black lines and the other colors of the lines. And the time scale, this is 5,000 year increments, 200,000 year increments, million year increments, 10 million year increments, 100 million year increments. So the data aren't kind of as precise time-wise. Going back hundreds of millions of years, there's not as precise of resolution of time as there is going back thousands or hundreds of thousands of years with those ice core records. And you can see that the fossil record and the ice core record of oxygen isotopes, they overlay very well. So we have a good confidence then that the fossils are indicating the same kinds of changes that we see in the ice cores more recently. This is the current interglacial cycle that goes back about 12,000 years. There's the last glacial maximum. about 18 or 20,000 years ago. And then we change time scale and have those alternations we talked about. And these alternations go back about 2.6 million years. The same types of glacial, interglacial alternations, although there have been glaciers at other times in Earth history too. Notice that it's thought that global temperature and global climate has been much hotter than it is right now for a lot of the geologic past, a lot of deep time, including periods when there were dinosaurs. So Triassic, Jurassic, Cretaceous, when there were dinosaurs, there would be ferns growing at the poles, much warmer overall than today, even hotter than that more recently than the period of dinosaurs. If you go back 300 million years ago or so, there's another period that's thought to be a lot like today in terms of global climate. It's a relatively cold period, and that was a period when there were glacial, interglacial alternations as well, just like today. And many of the rocks at the surface in Western Pennsylvania, much of the bedrock is about 300 or so million years old about this time, when there would have been sea level going up and down with those glacial, interglacial alternations. And as we'll see, Western Pennsylvania wasn't an area directly overlain by glaciers. It was near the equator, and so it was too warm for glaciers here, but the sea level changes certainly affected it. And there were glaciers in another part of the world at the South Pole at that time. Here's a reconstruction of continents from plate tectonics going back to the Pennsylvanian period, about 300 or so million years ago, a period when some of the rocks that are bedrock at the surface now in Western Pennsylvania were deposited. I'll point out the shape of North America here. Here you can see the curve of northwestern Africa, and those were together, and the continental scale collision created a large mountain belt that's a big subject of the talk about the Laurel Highlands. We talk a lot about that ancient mountain belt in that talk. The dots here, the green dots indicate where there are coals. There's the equator. So near the coals and in the basins that flank that mountain belt, there were a lot of peat swamps that formed, and when deeply buried, turned into coals. So this whole period of the Pennsylvanian, and then in the US, we say the Mississippian era before that, this Mississippian Pennsylvanian era worldwide is known as the Carboniferous period because there were so many coals deposited, so many peats deposited and preserved, turned into coals from this period. Now, before we move from this chart, I wanted to point out the assemblage of continents near the South Pole. And again, this was a time when there were glacial, interglacial cycles. Having continents at one of the poles makes this possible, makes it possible to build up a lot of ice on land and take that water out of the seas so that you can have big changes in sea level as the glaciers, continental scale glaciers, come and go at this time. A lot like has happened in the last 2.6 million years. This is a look at estimates for carbon dioxide going way back before we have ice cores. We only have ice cores that go back a million years or so. There are a few that are a little bit older than that, but not more than a couple million years. So these are from other proxies of CO2 concentration. So they're fuzzy. They're not precise going back. But in general, you can see that people think on this one, present day is on the left, going back to the right, back in time, hundreds of millions of years. When there were dinosaurs, people think CO2 was a lot higher. Remember, that was a hotter period. And here's that period in the Carboniferous. There's 300 million years ago, when it's thought that CO2 was relatively low in terms of Earth history, kind of about as low as it's been the last few million years. And an interesting hypothesis. So this is just an idea as to why CO2 might have been especially low at that time. But an idea is that there was so much sequestration of carbon in coals during the Carboniferous that it actually dropped CO2 globally and may have precipitated those glaciations that we talked about. So that's a kind of an interesting idea for why CO2 might have been low then, similar to it being low in recent millions of years. This is a closer look at CO2 more recently. Now we've switched it up, and present day is on the right, going back in time to the left. And you'll recognize that the vertical axis is CO2 concentration, and you'll recognize this shape being from those ice core bubbles in the ice core, so direct measurements from those. And then going back beyond the ice cores here, back farther in time, the CO2 estimates are from proxies. These two are geochemical proxies that indicate pH of seawater, which is related to CO2 concentration in the atmosphere. The one I'd like to talk about is easier to visualize though, and it's from stomata, or the pores in leaves, which you can see in fossil leaves too. So you can count these, the density of these pores going back in time in fossil leaves. A plant doesn't need as many stomata if CO2 is high in concentration in the atmosphere. It doesn't need as many to breathe, needs more to breathe if CO2 is low. That's a well-known effect that's been applied to fossil leaves. So the green diamonds here, although they're kind of not a super precise measurement, give some indication of general trends in CO2. And having looked at these proxies, CO2 today, actually, this chart also is a few years old. CO2 now is about 410 or 15 parts per million, as I said. And the last time it looks like there were at least some periods when CO2 was that high was close to 3 million years ago, when it was a few degrees C hotter overall, we think, and sea level, at least at times, was 5 to 25 meters higher than today. And as CO2 will surely increase in the scenarios ahead, you can see you have to go back even farther in time to get CO2 concentrations much higher than that, and that sea level was even higher and the Earth was even hotter than 3 million years ago. So just a little perspective on CO2 and sea level and Earth history. Now the climate modelers, when they look at possible scenarios ahead, they don't talk about sea level rising, more than a meter or so in the next 50 or so years. They don't talk about changes this drastic in the next 100 years or those kind of short time frames. But I'll just point out that last time CO2 was this high, sea level was quite a bit higher. And there are nonlinear effects, like ocean circulation patterns can suddenly stop or stop alternating. And there are a lot of other nonlinear things in Earth climate systems. Okay, I promised to talk about those long-term natural climate cycles. And this will help introduce the cycles that people think caused those alternations in glacial, interglacial periods in the last couple million years or so. There are three main cycles of Earth's orbit around the sun and how solar radiation hits the Earth. One is precession. If you spin a top, if you think of the top spinning and its axis kind of slowly revolves around, that's precession. And Earth's axis does the same thing relative to the sun, with a precessional cycle of about 21,000 years. Obliquity is the tilt of Earth's axis, so the angle of Earth's axis relative to the sun, and that has a cycle of about 41,000 years. And then there's an eccentricity cycle, how oval versus round Earth's orbit is around the sun overall, and that has a periodicity of about 100,000 years. And those have all been happening all through Earth history. They're natural cycles. Here's some rocks in the photograph in the lower left. There's half a meter for scale, that black line. These are 93 million year old limestones in white and shales, lots of clay in those in gray, that were deposited in a saltwater seaway in central Colorado, again, 93 million years ago. And these were described by a really prominent US geologist more than 100 years ago as potentially reflecting these types of climate cycles. And now we think that those interbeds reflect climate cycles in the range of 40 to 100,000 years, these Milankovitch cycles of obliquity and eccentricity. So the chart in the lower right indicates, if you take these cycles of tilt, eccentricity, precession, they're all happening at the same time. They interfere with each other in complex ways through time. So that if you looked at how much sunlight, for example, was hitting Earth, say at 65 degrees north, it's a pretty complex pattern. And it would affect climate in different ways, depending on how the continents are arranged and the ocean circulation patterns. So all of that's a pretty complex story that geoscientists are still working on understanding in detail for much of Earth history. But when you look at those ice cores and look at oxygen isotopes there in green, or you look at the marine microfossils that show the same climate pattern, you can see these clear 100,000 year cycles going back a million years with probably a higher frequency cyclicity superimposed on it from these other orbital cycles. So those are the cycles that are thought to be reflected in the glacial interglacial periods. This is another look at climate. This time it's a linear time scale, so it doesn't have changes. And today is off on the right, going back in time to the left. There are the oxygen isotopes. This time they're just from the microfossils, so they go back millions of years. And you can see those 100,000 year glacial interglacial periods in this proxy for temperature. And then about a million years ago or so, it flips to the 41,000 year cycle controlling these glacial interglacial periods. And there's really not, I think, a strong consensus on why that flipped happened at that time. So I won't try to explain why, but it's just an observation that it did at this point. This goes back farther in time, again, using the same source of data for a climate proxy. And I just wanted to point out this spike between the Paleocene and Eocene periods called the Paleocene-Eocene thermal maximum, when it appears that global temperature went up really quickly for a little while and then went down really quickly. So special events like that in Earth history, geoscientists are studying to try to understand what could possibly happen in the future with Earth, with the rapid changes that we're seeing both in atmosphere and in climate. Okay, now let's get back to glaciation. And in this reconstruction of glaciers from the last glacial maximum about 20,000 years ago, I'd like to focus on the polar areas. And you see that they've reconstructed how thick they think ice was. This is in meters. So it's up to 4 kilometers of ice, where there's dark blue here in Antarctica, but also in Canada. You can see Greenland here, Northern Europe, and Russia. And if we move down to our region, the south shore of Lake Erie would have had a kilometer or so of ice in typical reconstructions of ice thickness. So certainly plenty thick ice there in terms of blocking off rivers that formerly drained to the north. That's a big subject of the Allegheny and Upper Ohio Valley talk, one of the other of the 6 series of talks. Looking at North America, in Canada, these glaciers have come and gone multiple times in the last couple million years. And they've really scoured down to very old bedrock in much of Canada. And the area shown in brown here is an area where glaciers did scour bedrock, but there still are sedimentary rock layers preserved there. So not as deep of scouring. And there also are lots of glacial deposits scattered around, veneer of that on top of bedrock in the area shown in brown. And then the area south of the brown is beyond where glaciers went. And we talked in the rivers talk about how the glaciers controlled where the Ohio River now runs. So if you want to learn more about that, take a look in that talk. Okay, here's a similar map, but this time the blue lines indicate the directions of ice movement, people think. Some of those are based, or many of those are based on direct measurements, scours, grooves, and small valleys scoured into bedrock landforms of streamlined landforms of soft sediment shaped underneath glaciers, those kinds of things. So you can see the general movement of ice. When ice comes down to its snout, then the ice melts and the ice carries along rocks, sand, clay that it's scoured out of the bedrock. It carries it along in the bottom of the glacier, mixed in the glacier. And then when the glacier melts, that sediment is left behind where it melts. And there also are often glacial deposits on the bottoms of glaciers. That's called glacial till, really mixed up sediment that's been ground up under the glacier and picked up from bedrock and carried along. That's glacial till. And there's some examples of finding bedrock in one place, and then finding it in the glacial deposit somewhere very far away. And the one I wanted to share with you is a very cool one, I think, from the Huron supergroup. These are rocks in outcrop in Canada, north of Lake Huron here, that are over 2 billion years old. This itself is a glacial deposit from one of the really old glaciations in Earth history. This is a till deposit with, it's not very well sorted by water. It's all mixed up grain sizes, clay, sand, cobbles, small boulders, many different rock types that were picked up by glaciers along the way. And people have found that same rock type in glacial deposits, in glacial sediment in southeastern Ohio. So there are a lot of examples like this. I'll show you later some of the same kinds of rocks carried by glaciers washed out on the shoreline and along Lake Erie. Many of those rocks having come from far up into Canada. I haven't found this yet. I'd love to find this kind of rock on the Erie lakeshore in Pennsylvania, but I haven't found that. I found other rocks that come from other places in Canada, but not that one yet. Okay. I wanted to show this map of glacial deposits in Ohio because it's such a great map. And this is also shown in the rivers, the Ohio and Allegheny Rivers talk. There's more explanation of it there, but this is glacial deposits in Ohio. These brown colors are from very old glaciations down near Cincinnati. Some of the oldest glaciations went at least that far south. The youngest glaciation, going from that last glacial maximum 20,000 years ago, from the maximum, the glacier started to retreat. And when the glacier paused, when the snout of the glacier paused for a while, that conveyor belt of sediment that is a glacier would have carried sediment down and formed a small ridge. So these green bands are moraines, they're called, that hill deposit at the end of the glacier, where the glacier retreat paused for a while, it built a hill of sediment, then the glacier retreated again, built another hill, retreated again. So you can see that stepwise retreat here and get the concept of moraines as a place where the glacier paused in its retreat. Just to be more complete in the explanation, the blue colors are lake deposits from glacial ages. So we'll talk about the Great Lakes quite a bit, but you can see that there are some lake deposits from glacial ages that go way beyond the present shoreline of Lake Erie, go way into Ohio. So clearly the ancient glacial lakes from the last retreat, at times the lake was much higher than today. Also, you note that these river valleys have lake deposits in them, and those are discussed quite a bit in that valleys talk, the Ohio and Upper Allegheny valleys talk. There's a lot about those. Okay, Pennsylvania glacial deposits. These colors, this brown and green and these blues, indicate different ages of tills, of different ages of glacial deposits as glaciers came down into Pennsylvania and then retreated, came down again, retreated multiple times. The dashed line is approximate limit of glaciers. So there have been things like boulders from Canada found out in front of these more continuous till deposits from some of those old glacial deposits, but the rest of the deposit has been worn away by erosion, washed into rivers and streams. And the yellow here indicates water washed glacial age deposits. You can see there's a lot of that along the lake plain here, along Lake Erie, including Presque area. And also there are glacial age sands and sediments washed into rivers and streams. Here you can see from the glaciers that came into northeastern Pennsylvania, there are glacial age sediments that washed into the Susquehanna River Valley, for example. And the red circles or ovals here indicate the two bike trails that will cycle on Presque, and then the Stavich Trail here in central western Pennsylvania and eastern Ohio. Those glaciated areas have very different habitats too. The plants, animals that live there are different than other regions. And if we focus on northwestern Pennsylvania and the glaciated area, you can see that it's a mixed woodlands plains there. The topography is more muted because the glaciers, as they flowed across the landscape, helped rub out some of the topography, make the topography flatter, but also they left behind glacial deposits that helped fill in valleys. So it's a smoother topography. And because some of the topography is still there from when the glaciers left, that streams and rivers haven't incised into it yet, there can be natural lakes in those areas in northwestern Pennsylvania. And there can be natural bogs too, because it's just the undulating topography that was left behind by the glaciers, not formed by erosion or incision by streams and rivers. So some very different habitats are found in northwestern Pennsylvania than farther south. Here's an elevation map that's pretty familiar if you've looked at others of the talks. And you'll see there's the Allegheny River Valley, steep-sided valley up to 400 feet deep in places. And look at this area around the Mahoning River Valley where the Stavich Trail goes. And away from the very more recent erosion of the streams and rivers, it's a pretty muted topography, not nearly as sharp hills as these areas that are beyond where the glaciers came. So the edge of the glaciers was kind of right about here, and you can pick that boundary just by looking at where the landscape is more flat and muted versus being a lot more hilly. And then there's the lake plain right up against Lake Erie, and Presque is attached to that lake plain. And there's a lot more description of the origin of all these landforms in the Laurel Highlands talk, the talk that focuses on part of the Great Allegheny Passage as well as the Indian Creek Valley Trail. And I encourage you to look at that if you want to learn more about why the landscape is the way it is through the rest of the state and surrounding area. There's a geologic map. Again, this is discussed in that Laurel Highlands talk as well. I'll just point out that around the Stavich Trail, there are bedrock at the surface of Pennsylvanian and Mississippian ages in that area. And along the lake plain up here, there's bedrock of Devonian age, upper Devonian age, including lots of shales that were deposited in a seaway during the upper Devonian. So now let's move to the Great Lakes and look at the shape of these. It's a kind of an odd shape, don't you think? And I'd not really thought too much about it until I realized that there's a reason why these are shaped the way they are, but it's kind of an odd shape. And the reason I'm showing this particular chart is because it shows the connections that they're all connected today. Lake Superior flows into Lake Huron and Lake Michigan, and Lake Huron and Michigan flow into Lake Erie, which flows into Lake Ontario, flows through the St. Lawrence Seaway into the Atlantic. So they're all connected today, but it wasn't always that way through their history, even only in the retreat of the last glaciation. And probably the rest of the time I talk about the Great Lakes, I'm going to talk as though they were only formed by the last glaciation, but that's not necessarily true. There were multiple glaciations, as you saw, that came across this area. So probably, although their history, even in the last 20,000 years, is pretty complex, it probably is even more complex because there were lots of generations of glaciers that passed across this area. Okay, now we have both a map and a cross section. And in the cross section at the bottom, you can see we go from Lake Superior flowing down to Lake Huron and Lake Michigan, which are at the same level. Lake Michigan here and Lake Huron connected. There's Georgian Bay, part of Lake Huron. And then those flow into Lake Erie. And then Lake Erie flows, the Niagara River goes across the Niagara Escarpment at Niagara Falls, and then down to the level of Lake Ontario. And then we go down the St. Lawrence River to the Atlantic Ocean. So they're all connected today. The map shows watersheds. So the blue are watersheds that flow into Lake Erie, and the drainage area of Lake Erie watersheds really isn't a very big area. So the amount of water coming into Lake Erie from Lake Huron and Michigan is about the same as water that's flowing out of Lake Erie into Lake Ontario. So if it wasn't for that lake water coming into Lake Erie, it really wouldn't be giving water to Lake Ontario. And the level of Lake Erie would have everything to do with how much rainfall and evaporation there are in its watershed. So at times when actually Lake Erie didn't receive water from the upper Great Lakes, at times Lake Erie was much smaller than today. And as we talked about before, there were other times when it was much higher than today. It's been both higher and lower than today in its past. And I wanted you to see the watershed so you can get a clear idea of how that could be. Just a reminder of the directions of flow of glaciers from Canada into northwestern Pennsylvania, as well as northeastern Pennsylvania, generally flowing from the north, they're thought to have flowed along Lake Erie and down into Ohio and beyond in these different lobes of glaciers. And now I'm going to talk about different rock types. And we need this to understand the shape of the Great Lakes. So we'll come around to that eventually. But first, to introduce the main types of rocks, sedimentary rocks are formed by particles laid down layer by layer by layer. When deeply buried, they can turn into rock. If rocks are super deeply buried, like maybe 30,000 feet or more, they can be recrystallized into metamorphic rocks, crystalline rock. And when there's really hot liquid rock, magma down deep, that can cool and form crystals. If it cools slowly, it forms large crystals like granites. If the magma comes to the surface and flows as lava or spews out of a volcano in the air, it can make volcanic rocks that have very tiny crystals or no crystals. It's just like glass. So igneous rocks are formed from magma or lava. Metamorphic rocks are recrystallized, and sedimentary rocks are the sediments at the surface when very deeply turn into rock. Here's some examples in the center and left of sedimentary rocks from our area in Western Pennsylvania. Sandstones, lots of sand grains, feels like sandpaper, a little bit finer grained. Siltstone still feels rough, but not visible sand grains. And then a mudstone or shale made up largely of clay, smooth to the touch, very fine grained, not resistant to erosion. Sandstones with lots of quartz resistant to erosion form the ridges, form valleys. A limestone, calcium carbonate, those can be from when the seaway came into the area and there were a lot of organisms living in the seaway, producing calcium carbonate that turned into rock later on, or they can be deposited in freshwater lakes. There's coal from a peat swamp. I put an ironstone in here because that's so important to the iron resources. Often those are in nodules found within shales in our area. In one of the limestones, there's a layer of ironstone on top of it. That was a pretty good resource. And then this is a rock kit that I give to people to learn rock identification in our area. It's handy to be able to identify man-made materials like slag, concrete, and brick as well. So these are common sedimentary rock types in our area. These are metamorphic rocks from Pennsylvania too. These are collected along the Lake Erie shoreline. They've been washed out of till, rolled around by waves on the shoreline and rounded and polished where they're hard rocks. So these are metamorphic rocks and igneous rocks that came from Canada, carried down by glaciers, and then washed out of glacial deposits onto the Erie lakeshore beaches. And I just love the patterns in some of these rocks. These are high-grade metamorphic rocks. This is an Augengneiss, Augen meaning eye in German. So they're beautiful gneisses up there, high-grade metamorphic rocks. Some of them have lots of garnet, up to 20-25% garnet. This is a large garnet in a metamorphic rock. So these rocks, again, were buried so deeply that they've recrystallized and are at the surface now in Canada, picked up by glaciers and carried down to Pennsylvania. These are igneous rocks, same source. Granites, you can see the large crystals here from the magma that cooled slowly in the earth a long, long time ago up in Canada, and then made its way to the surface. Layers on top were all eroded away through a long period of time, not just by glaciers in the last 2 million years, but over many hundreds of millions of years, and carried down by glaciers into Pennsylvania and washed out on the beach. So here's why we learned those different rock types. This is a geologic map. It's a map of ages of rock layers at the surface today, of bedrock at the surface. You can see the outline of Pennsylvania in gray here. And these blue, gray, purple colors with long bands of color, those are different sedimentary rock layers. Ordovician are older rock layers, Silurian are younger, Devonian, younger, Carboniferous we talked about are younger rock layers. So that's a sedimentary rock cover, layers of sedimentary rock that sit on top of crystalline older rocks underneath. So here in this part of Canada, southern Canada has sedimentary rocks too, but farther north in Canada, it's all igneous and metamorphic rocks. These black lines are faults. Those are sharp boundaries between different rock bodies where rocks have moved one against another, and lots of different types of igneous and sedimentary rocks through these areas. This is the Adirondacks. This has crystalline rocks as well, lots of metamorphic rocks, maybe some igneous rocks too. And I've put ages of these Precambrian rock, Precambrian being before the Cambrian. Cambrian is another common sedimentary rock layer here. So these are in billions of years. The GA is billions of years ago. So the Adirondacks rocks there are about 1 billion years old. These rocks over 1 billion years old. And then across this line, much older rocks, rocks over 2 billion years old. This was more of a core part of a continent. These rocks were accreted onto the side of that continent. Then younger rocks were accreted onto the side. That's a process that happens. So continents both split apart and make smaller continents, but then they crash together and parts of them accrete and form a bigger continent, and they might split in a different place later on. So a profound boundary here between sedimentary rocks and crystalline Precambrian rocks. Within the sedimentary rock cover, I talked about the upper Devonian here. In the Devonian, there were deltas shed off a mountain belt to the east here. So there were sands and clays shed off that mountain belt, a coastal plain. But there was an offshore seaway. There was an interior seaway where lots of clay was deposited, some thin sands, but lots of clays that form shales, which are soft and easy for glaciers to scour away. So this light blue is a band of upper Devonian age sediment that glaciers have scoured away all through the area of Lake Erie, Lake Huron, and Lake Michigan. This is a sedimentary basin, the Michigan Basin. These are younger rock layers, older rock layers. And so you can see that the shape of Lake Michigan and Lake Huron here is a good indicator of where that upper Devonian shale was at the surface that was so easily gouged away, eroded away by glaciers and carried off as glacial sediment farther south. Same thing with Lake Erie. It reflects where that soft upper Devonian shale was scoured away. Silurian rocks have some harder rock layers. A prominent one of those is a dolostone. It's like a limestone, but it has a lot of magnesium instead of calcium. It's harder. It's more difficult for rainwater to dissolve it. It's a relatively hard rock, and that forms the top of Niagara Falls. There's a shale underneath that forms the plunge pool there. So the Niagara Escarpment is formed by these Silurian rock layers that are more resistant to erosion. And you can see that escarpment goes all across. Here separates parts of Lake Huron, Georgian Bay, from the main part of Lake Huron. You can see it's here. They even talk about the Niagara Escarpment in Wisconsin. This is Green Bay, and you can see this peninsula separates Green Bay from the rest of Lake Michigan by that those harder rock layers in the Niagara Escarpment. So that's why Georgian Bay looks the way it is. It's on the other side of that escarpment. Lake Ontario also, and there's an Ordovician shale. It's red in color. So I'll show you some bluffs here that are largely made up of gouged Devonian shale that are gray, but this shale is red. So the bluffs along the shoreline of Lake Erie, Lake Ontario are red from this soft Ordovician shale that was gouged out in these areas. So Lake Superior then is the last one that we have to talk about. And you can see it's in the Precambrian area. It's not in this post-Cambrian sedimentary rock cover. So here was a basin that was formed as the assembled continent a long time ago, more than 500 million years ago, started to try to rip apart. So it formed a sedimentary basin as it started to try to rip apart in a mid-continent rift, we call it. Sediments poured into that basin. There were lots of sands that were poured into that basin, then were buried and turned into sandstone and metamorphosed a bit into a metamorphic rock. But that basin is flanked by igneous rocks, crystalline rocks that are harder to erode and were harder for the glaciers to gouge out. So the shape of Lake Superior largely reflects the shape of that sedimentary rock basin, that rift basin of Precambrian age. So there you have it. The reason for the shapes of the Great Lakes, including Lake Erie. When you look closely at the bathymetry, elevations of the floor of these lakes, you can pick out some of the more resistant sedimentary rock layers as ridges underneath the lakes. And you can also pick out places where glaciers gouged grooves into those lakes as they flowed. And notice Lake Erie is the shallowest of the Great Lakes. It has a deeper part, though. Pennsylvania part of the Lake Erie shoreline is right about here. Presque is right about there. And there's a deeper part of Lake Erie to the northeast. And we'll talk about that boundary between those in a different map. A little bit about the formation of the Great Lakes since the last glaciation 20,000 years ago, as the glacier was retreated. And this is only 4 snapshots. It's a much more complicated history than this, but I think these 4 snapshots will show you the basic concepts here. So here you can see 14,000 years ago, there's still ice in this part of Lake Erie, what's now Lake Erie. Presque would be about here. This is when the ancestral lake here was much higher than Lake Erie is today. There's no outlet in this direction and a much higher lake. There was an outlet for Lake Chicago, you know, what the footprint of what became part of Lake Michigan later on. And ice retreated a bit more here. And in this reconstruction, there's some connection between these lakes. In this reconstruction 7,000 years ago, there's not drainage from the upper Great Lakes into Lake Erie. They actually drain into the what's now the St. Lawrence Seaway, along with Lake Ontario draining that way. So there's not water coming in from the upper lakes here, and the level of Lake Erie was actually a lot lower than today. So the level of ancestral Lake Erie has been both higher and lower than today through the past. And this connection has gone away as the land has rebounded after that thick ice went away. The land actually popped up more than 100 feet, rebounded enough to affect drainage patterns quite a lot. So you can see that there's been a lot of change in the drainage patterns here, and Lake Erie has been both higher and lower than today. Okay, let's zero in on our area of interest. There's a map of Presque. There's a bike path that makes a loop around there. And part of the loop is a bike path that's separate from the road. But as you can see in the picture that includes the lighthouse on Presque Isle, part of the bike path is next to the road. The speed limit, I think, in the state park here is 25 miles an hour. So, we should be safe, although we'll watch for the traffic behind us too. So we'll do that loop around Presque Isle, and you can see clearly the shape of Presque Isle today. There's a scale down at the bottom, 2.5 miles. And that shape is thought to have changed a lot through time. It's a sandy peninsula. There are dominantly storm winds from the west, waves from the west that help shape this peninsula and have changed it quite a bit through time. Beach processes are relatively rapid in geologic terms. I promised a more detailed map of the floor of Lake Erie. So here's a bathymetric map of Lake Erie. There you can see Presque Isle is right here. So here's the deep part of the lake to the northeast. And look at the really shallow part of the lake through here. The same kind of thing happens here, where there's actually are some islands. So those are both places where it's thought as the glacier here retreated, it paused for quite a while, gouged out a lot of sediment here deeper and left sediment behind in front of it, gouged out a lot more sediment here, left a moraine of sediment at its snout in front of it. And it's this moraine that the wind and waves, the waves wash the sand out of that moraine. And that's where the sand comes from that forms Presque Isle. That's why there's not another peninsula like that along here. It's because it's sand that's washed out of that moraine. And look at the northern shore. We don't often in Pennsylvania look at the whole lake, but you can see that the same sort of thing has happened in Canada with a very prominent peninsula just down from the direction that these storm wind-driven waves would carry sand along the shoreline. So there you have it, origin of Presque Isle and why it's such a unique feature along the shoreline. Here's the topography in detail of Erie, the Lake Erie watershed in Erie County. And you can see the low elevations pretty flat on the lake plain here. There's Presque Isle. And a couple of key features of the lake plain also are these streams that have been sized into it. There's Elk Creek, this is Walnut Creek, and there's some more subtle features. See how there's a very subtle ridge along here? Those are ancient beach ridges. I'm going to actually show you a picture of one of those and a better map of those. These creeks are famous as steelhead fisheries. Steelhead are trout that live most of their lives in the lake. They grow to be quite large, and they'll run up these streams, and people fish for them. It's quite a thing to see. They're really large trout. The beaches. This is a map from an undergraduate thesis at Mercyhurst, and they used radar images, very detailed images of the surface of the topography of the land to closely identify these two beach ridges, which are thought to be 13,000 years ago, and then another beach ridge for so-called Lake Warren, 12 to 13,000 years ago, a younger one. And I promised a picture of one. So here, this beach ridge comes out to what's now a lakeshore bluff. And the lakeshore retreats typically 1 to 3 feet per year. So the lakeshore through hundreds or even thousands of years surely has retreated quite a bit. And so this beach ridge has been cut off and it's gone now. But we can see it along the lakeshore here in Lake Erie Community Park. This is water washed sand. It's very fine grained sand, but water washed. There are lots of laminations and cross laminations from the beach to, processes, the water processes that washed this sand when this was a beach. It makes the lakeshore bluff here about 20 feet higher than it would be otherwise without having a beach perched on it, on top. And below that, there's a lot of this sand that's kind of washed down the slope here, but the actual sediment that's in place is gray. It's a medium gray color. Here's a picture of the same sediment from farther down where it's safe to look at it. And it's till, like we talked about before. It's ground up clay and sand and bits of rock and pebbles and cobbles and boulders all mixed together, not water washed. That's from underneath a glacier when the glacier was here. And then again, a beach ridge of water washed sediment on top. So there you get to see these beach ridges. There's the location of Presque we talked about its origin, and you can easily pick out these beach ridges. There's low ground on both sides of them, both right and left as you're driving along. And often there's agriculture on them because they make well-drained soils, unlike the till, which makes poorly drained soils swampy, not great for agriculture. Here's a picture from a little to the west of Presque along the lakeshore. So you can see the till here, a glacial deposit, medium gray. There's Devonian bedrock. It's this type of rock that was ground up by the glaciers and makes up a lot of the till, along with sands, pebbles, cobbles, boulders that were carried from as far north as way up into Canada. And these, the retreat of the bluffs here, the pebbles, cobbles wash out onto the beach. They roll around. You saw some examples of those earlier, igneous and metamorphic rocks. And that's what this is. This is the mouth of a stream that's left the bedrock exposed here. And these are the kind of cobbles that have washed out of the till and roll around on the beach here as the waves come and go. Here's another example of this with a big limestone boulder that was carried by a glacier from farther north. And these limestones, large and small, often have fossils in them. That particular one had a pretty nice set of fossil sponges in it from hundreds of millions of years ago. Another neat feature of the lake plain are those incised streams. This is Elk Creek, a famous steelhead fishery. If you look at it more closely, I count up to 5 benches or terraces as the stream has progressively cut down through time. There's a lot of discussion of river benches in the Allegheny River in that talk, but there's some pretty nice ones here along Elk Creek. And this is the Devonian shale bedrock in this area. And it's a spine of bedrock called Devil's Backbone, where some crazy person has walked out here and taken a picture. Not something I would do. This is a place where Little Elk Creek makes a really sharp turn around that spine of Devonian shale. So it's a pretty neat and prominent type of landform here. Another amazing thing that happens, this is Presque Isle. Sometimes, not every year, but sometimes in the winter, under the right conditions, you can get ice volcanoes build up. So here, the lake is not completely frozen. There's open water and there's an ice shelf. So when there's strong winds and waves that drive into this ice shelf, the waves go underneath the ice shelf. And when they hit breakwater or hit the shoreline, they can cause waves that go high into the air. And when the air is really cold, that lake water freezes around it. So this is an ice volcano that's caused by those conditions. And when there would have been strong waves here, there would be water spurting out of the volcano and adding to its sides. So ice volcanoes are a pretty special feature that you need special conditions to get. You don't get them every year along the Erie Lakeshore. This is another really cool thing that's especially prominent in the spring. So here along the lakeshore, here's till we talked about. There's a sandy water wash deposit on top of it, more pure sand, lots of clay in the till. And you get lots of ice buildup here through the winter. And when that starts to melt, that's one of the erosional processes that makes the lakeshore move back typically 1 to 3 feet per year. When the material that is coming onto the beach is mostly from the till or entirely from the till, and it's loaded with clay, it makes these really cohesive, amazing debris flows. Where you get material that's mostly coming from the sand, you tend to get more clear water flows. You can see little individual grains flowing along the bottom here. And so this is what we would call a tractional flow. It looks like a delta. looks a lot like a typical delta. And there are ones that have a mix of those sediment types, a mix of sand and cohesive clay, and those form a really prominent other end member, these levied channels with these mouths of them, and these little fan or debris flows. And these look a lot like submarine fans that are formed offshore in really deep water, with a levied channel up dip here and the slurry flowing down, and where you lose that channel, then locus of deposition. So some really neat sedimentary features along the lakeshore, especially in springtime when there's the ice on the bluffs is melting. Okay, let's look now at the Stavich Bike Trail and talk about interurban trolleys. There's a picture of the Stavich Bike Trail. It goes right along a very busy railroad line. And the Stavich Trail was not a railroad line, it was a trolley line that served Youngstown and Newcastle and connected those up. It was known as the Mahoning and Shenango Railway and Light System, then the Penn Ohio Electric System. These were called traction electric rails. The end of this came with automobiles, and it was replaced by a bus service. It's a 10-mile long trail, a nice trail, and you can see the end of it in Ohio is in this picture. Here's a picture of one of the trolleys that went along that railway system. And there's an elevation map showing the area of the Stavich Trail in this heavy red oval. Other of the trails that we'll ride are in these lighter ovals. And you can see the more muted landscape here where it was glaciated compared with steeper valley edges and some deeper valleys along the Allegheny River system here than in this area. So a more muted glacial landscape. And here you can see our start and end points. We don't actually start in Newcastle or end in Youngstown. The 10-mile Stavich Bike Trail is in between those two. And here's the strongly erosional Mahoning River Valley. This is a map where my bubble moved. So let me take that bubble away so it's not so prominent. And I'll point to where that is. Okay, so this is a map of interurban trolley lines in the Midwest and going into Pittsburgh in Western Pennsylvania. And the Stavich line, it goes from Newcastle, in between Newcastle and Youngstown. It's right here. That's an interurban trolley. But at one time, you could ride on these interurban trolleys all the way from Pittsburgh to Cleveland, to Columbus, to Toledo, to Detroit, to Fort Wayne, all the way to Chicago on these interurban electric trolley lines, to Indianapolis, to Cincinnati. It was an amazing system. This was kind of free enterprise at work. These were privately held investment opportunities, and there were lots of them. Just like in Pittsburgh, originally there were scores of trolley lines that eventually became consolidated. So this interurban trolley system was just amazing in its heyday from the 1880s into the early 1900s, before it was replaced by cars and buses, which, by the way, ran on publicly funded roadways versus these private enterprise interurban trolleys. So an amazing system. So hopefully you've got a lot more awareness of the two of the great bike trails in Western Pennsylvania. We've learned a little bit about climate, both in glacial, interglacial periods in the last couple million years, as well as 300 million years ago, and in between and longer, and including the time when bedrock in Pennsylvania was formed. We've learned a lot about the Great Lakes here, including Lake Erie and the formation of Presque. And you got to see that the Stavich Bike Trail is really unusual because it's a line of one of these interurban trolley systems. It also is one of the few bike trails around that crosses a state boundary. And this is the fifth of the 6 talks I plan to make. Still have the Wilds one yet to make. the 3W Wilds talks are in October, so it may be a little while before I create that one and post it online. But I hope you've enjoyed the presentation. I hope you've gotten some things out of it, and I hope to see you out on the trail. If not with Venture Outdoors, then out on a trail on your own or with a group. Take care.